Now, there's more than one type of machine learning, and again, it's good to be aware of what the main types are. The examples that I've been giving so far, and that little diagram that I had with the box and the computer and the program and whatnot, these are really examples of what is called supervised learning, also known as inductive learning. This is the largest subfield of machine learning. It's the most mature subfield, and it's the one that's most widely used, so it's the one that we will spend most of our time on. So what is it? This is learning where, you have supervision. This is why we call it supervised, where the learning program is given examples of the desired output. The learning program is told, this is spam, this is not spam. This person has AIDS according to this test, this person doesn't. Okay? This is the direction in which you should drive in order to stay on the road. Okay? So obviously learning with supervision is much, much easier than learning without supervision. Okay? It's still plenty hard, and we'll see what some of the issues are that arise. But it's certainly a much more solid technology at this point and easier to deploy. The problem with it, of course, is that it's hard to come by supervision. Big data is all over the place. Generating oodles and oodles of data can be done very easily in many domains. Labeling the data still has to be done by humans. In cases where the labels for the data are generated automatically, for example, this stock, I predicted that it would go up tomorrow, and tomorrow it did go up. Those domains are great because you can really, kill them with supervised learning. But in many, many domains, you don't have supervision. And so then what you do is you have to learn from data where you yourself have to figure out what the output is. Okay? An example of this is clustering. For example, a very popular exercise in marketing is to cluster your customers. Right? Nike's two main types of customers are teenage boys and middle-aged women. True fact. It's very important to realize that these two clusters exist because they have very different tastes. A marketing campaign geared to teenage boys is unlikely to appeal to middle-aged women and vice versa. So clustering can be really, really important. But people in general will not tell you in advance what those clusters are. You have to figure them out, right? Also, another popular example of this is clustering text, right? I have millions and millions of documents in my company, right? How do I organize them and find them? Well, maybe I can form a hierarchical clustering of them, right? Things like Yahoo and DMOZ, right? They are hierarchies, right, of documents or of web objects, right? In most cases, in the beginning, in the early days, these were done by hand, but pretty soon they started using machine learning. Use machine learning to figure out what this hierarchy is. And then once you have the hierarchy, when a new document comes along, you can say like, oh, this one is about sports, or more specifically, it's about baseball. Or, even more specific, it's about this or that. Okay? So once you figure out what the outputs are, then you can, figure out how to turn the inputs into the outputs, and then in the future, you produce those outputs in response to the inputs. Now, unsupervised learning is also, a long-standing field of machine learning, but obviously it's much harder. It's much harder because you have less information to work with. It's also much harder because it's much harder to tell what is a good result and not. In supervised learning, it was spam and you predicted it was. That's a success, right? You gave a credit card to this customer and she paid, her bills on time. In fact, the best credit card customers are obviously not the ones who pay the bills on time. Are the ones who are always a little bit late and they accumulate these fees and whatnot. Right? The ones who don't pay are bad. So, but you have the supervision to produce that. Okay? So what do? Well, this is where semi-supervised learning comes in. It is often the case that you can't afford to label all the data, but you can afford to label some of it, or you have by luck some subset of the data that does come with labels. And so what you want to do is you want to start with that small subset of the data that is supervised, and then you want to bootstrap from there to label the ones that are unsupervised. So use a small amount of supervision to, at the end of the day, do a large amount of unsupervised learning. And this can be amazingly effective because a little bit of supervision can go a long way. In fact, you could say that this is how most people learn most things, right? It's semi-supervised. They get a little, help from their parents and from their teachers, but then they're on their own. If they were completely on their own, they'd be in trouble. On the other hand, the parents and the teachers, can't be, on top of them all the time saying wrong, right, wrong, right. Okay? So we're not going to talk about semi-supervised learning here just because there isn't time for everything, but it's good to be aware that it exists because it might be just the perfect thing for your problem. Finally, there's reinforcement learning. Reinforcement learning is probably the most ambitious type of machine learning. AI types tend to like reinforcement learning a lot. It's also in some ways the hardest. The idea in reinforcement learning is that Reinforcement learning is not learning to make, point-by-point decisions. For example, is this stage interesting or not? Right? Does this patient have this disease or not? Reinforcement learning is like a real agent in the real world. You're making a sequence of decisions. You're playing a game, for example, or you're doing something over time. And it's only after you've made a bunch of these decisions that it becomes clear whether you were doing the right thing or not, right? At the end of the day, you win the game of chess or you lose. And then you have to somehow propagate this information back to those decisions that you were making early in the game, when it was not obvious at all whether they were going to be good or bad. Okay? So in a way, reinforcement learning is a kind of semi-supervised learning, because you only have a small amount of supervision, but it's distinguished by the fact that it is this sequential kind of semi-supervised learning. You're learning to propagate the results, the payoffs, when you finally have them, back to the decisions that you made earlier. Again, we're not going to be covering this topic because there's no time for everything, but it's a very interesting and large area of machine learning. It is by far the least used of all these types of learning. So, if you're looking for algorithms to use in practice tomorrow, reinforcement learning may not be your pick, but you should at least be aware that it exists because, it might. And in the future, there'll probably be better reinforcement learning algorithms that will be more widely used. Yes?
I have a question about the semi-supervised learning. I mean, I'm confused about if it is just learning with a smaller training data set, isn't it the same as supervised learning, just with a smaller training data?
No. So let me clarify this, right? So here's the idea, right? Suppose that you have a bunch of emails, right? Some of which are labeled as spam and some of which are labeled as not spam. This is supervised learning, right? Suppose none of them are labeled, right? Then you just want to cluster them into, good and bad emails, and maybe this will coincide with being spam and not spam, right? This is very hard. You have no labels. Semi-supervised learning is when you have three types of emails. Some are labeled as spam, some are labeled as not spam, and some are not labeled, right? So for some of them, you don't have labels at all. And what typically happens in semi-supervised learning is that you only have labels for a small fraction. So let's suppose, for example, that you were an email, and this is a real example in many cases. This is what happens. Now, let's say you're an email provider and you have 1 billion emails, okay? But you only have 100,000 of them labeled as spam, and 100,000 of them that for some reason you know for sure are not spam, right? So this is the semi-supervised learning setting. And the idea there is that you want to start out doing supervised learning, just looking at the ones that are labeled. But then from those you can bootstrap. You go like, oh, these emails here are not labeled, but they're very similar to the ones that were labeled as spam. So maybe those are spam. And maybe those are not spam. And now I have a larger training set. Some of it was induced by me, right? Until finally, hopefully, I've labeled the whole training set. When this works, it's extremely powerful. Of course, it's harder to make it work than fully supervised learning, but it's easier to make it work than fully unsupervised learning. More questions? Okay, so these are the main types of learning. In this class, for most of it, we're going to focus on supervised learning, also known as inductive learning, right? Since this is doing what the philosophers call induction. In some ways, it's the oldest, known type of learning. Towards the end of the class, we will talk some about unsupervised learning, okay? But for most of our time here, we're going to be talking about inductive learning, so let's start focusing on that. So what is inductive learning? What is the problem? Why is it hard, and how can we solve it? Here's a very simple definition of inductive learning. What I have is examples of a function. Each example has two parts. X, the input, and f of x, the output, right? X is your email, or maybe it's just a list of the words that appeared in your email. This is a common thing to do. And then f of x is, this is spam or this is not spam. Or it could be something like automatically picking which folder you want to refile the email into. Or automatically deciding what tags you want to label it with. Okay? In all cases, the key thing that defines inductive learning is the following, is that this is the test. When I see an X, when I see an example that I have not seen before, this was not in the data that I used to train my learning algorithm, my training data. Along comes a new example, right? A new email. Can I now classify, can I now predict this one correctly? Can I, for a new example X, correctly predict the value of the function? This is the problem and this is the challenge. I have to guess what the functions of unseen examples are. This is very different from almost everything else in computer science, right? In the rest of computer science, you're doing things that are more like deductive reasoning, right? I have these things and I know how to turn the crank to get this result. The crank might be very complicated, it might be millions of lines of code, but you only have to work on inputs that you know what they're going to be. Here, I basically have to make this leap from the examples that I've seen to the ones that I haven't seen. A new patient comes along, her combination of symptoms is different from any one that I've seen before. Can I still correctly predict what she suffers from? People are good at this. Traditional programs are not necessarily very good at this, but this is what inductive learning is all about. Now there's three main types of inductive learning. If the function that you're trying to predict is discrete, for example, spam versus not spam, or what topic is this piece of text on, then the problem is called classification. And each of the discrete outcomes is called a class, simply enough. If what you're trying to predict is continuous, like you're trying to predict a continuous variable, right? For example, there's this company here in Seattle that you may have heard of that predicts house prices, right? This is a very nice thing to be able to predict. This is a regression problem, right? The house price is a continuous variable. Regression is what most statisticians do for a living. People in computer science and in machine learning tend to be more interested in discrete things, so we will focus mostly on classification in this class. Nevertheless, for most classes of algorithms, there's a classification version and there's a regression version. So if you know one, usually with a little bit of tweaking, changing the evaluation measure and some things in there, you can see how you would get the other from the first. And we will touch on regression occasionally because, we want to have some coverage, but again, we don't have time for everything, so mainly we'll focus on classification. The other thing is when the final type of inductive learning is when what you're trying to predict is the probability of that instance. How likely is this thing to show up? Okay? Or how likely is this page to be interesting? Right? In this case, what you're trying to compute is a probability, and now this is called probability estimation. You could think of probability estimation as a kind of regression, right? Since a probability is a continuous variable, but it's a very special kind of regression because remember, the probabilities of all things have to add up to 1, right? So you're not free to just predict any old thing that you want, right? There's this normalization condition that you have to satisfy. So at the end of the day, the techniques that you use for probability estimation are often very different from the ones that you use for regression. And if you're trying to predict the probabilities of discrete outcomes, often the classification and the probability estimation go hand in hand. For example, you could build a classifier by building a probability estimator and then thresholding the probabilities. So I built something that predicts the probability that an email is a spam, and then I say, if the probability is above 0.5, then I predict that it's a spam, right? Or if I want to be more conservative, then I will predict that it's a spam if the probability is above, say, 0.8. Okay? So these tasks are different, but there's also relations between them. Questions about any of this? Okay, so that's the definition of inductive learning. Here's a preview of what we're going to do in this class. So as I said, most of the class will be spending on supervised learning. I believe it's very good to get your hands dirty right away. Start working with real algorithms and applying them to real things right away. Many machine learning algorithms are joyfully simple, at least the basic versions of them, and the basic versions get you very far. People often get intimidated when they see these very mathematical machine learning algorithms and machine learning textbooks with literally hundreds of equations in every chapter, right? There's equation number 11.647, right? But the truth is actually that is all icing on the cake. You can get a lot of the problem machine learning with much simpler things. So let's start studying some of them right away. So we will look at decision tree induction, rule induction, instance-based learning, basically one of these every week, Bayesian learning, or more generally statistical learning, neural networks, support vector machines, how to do ensembles of these things. We will spend a week on learning theory. There's a large literature on learning theory, and some people like to start with the theory. I actually don't think that's the best idea because you don't know the point of the theory in the beginning, and it's very natural to be alienated. What we're going to do is we're going to look at the learning theory after we've looked at a bunch of these things and seeing what the common questions are that arise. One of the themes here is that we're going to look at all these representations and evaluation functions and whatnot, but there's a set of recurring problems that keep coming up, like overfitting and the curse of dimensionality, independent of the representation. And so once you've seen that, I think at that point, hopefully you will be ready to can we really come up with fundamental notions of how we deal with these? And that's when we will dive into some theory. And we will focus on the theory that's useful, right? There's a lot of gratuitous theory out there, but that's not what we're going to do, right? we're going to do some theory that hopefully will really be useful to you in deciding, what algorithm to use and how to optimize it and whatnot. And then actually after that, we will look at support vector machines, because support vector machines are actually a machine learning approach that comes out of this theory. A lot of the approaches that we're going to see, they predate some of the theory that we're going to look at. The support vector machines actually come out of that theory, so that makes a very nice sequence. Also, some model ensemble methods came out of that theory. And then finally, we will look at unsupervised learning. Unsupervised learning is a huge field. We could easily spend the whole quarter on unsupervised learning. We don't have time to do that, but we do have time to look at the two main types of unsupervised learning and a few of the key techniques in each one. So even though we're not going to spend that much time on it in class, you will learn enough to go and apply this tomorrow if you want. And the two main types of unsupervised learning are clustering, which I already mentioned, and dimensionality reduction. The idea in dimensionality reduction is that there's two ways in which big data can be big, to oversimplify things a little bit. One is that you have a lot of examples, right? I'm Facebook, I have information on 1 billion people. Wow, that's big data. That's one dimension of big data. But the other dimension of big data, in machine learning terms, that means I have a lot of examples to learn from. But the other dimension is that I might know a lot about each one of these people. In fact, you could even argue that that's the big advantage that Facebook has, is that it actually has more information about any one person than Google or Amazon or any other of these companies. Okay? So in technical terms, we say that you have many dimensions for each example, right? I have not 1,000 variables, I might have hundreds of thousands or even millions of variables. And this really is a brave new world. If you look at traditional statistics, what's considered high dimensional in there is like 10 dimensions. Right? In fact, in the old days, anything above 3 dimensions, which is what our world has, was considered high. 100 dimensions in machine learning today is like, what is 100 dimensions? 1,000 dimensions is starting to get interesting. 100,000 is big data. Okay? But now if you have all those dimensions, this is going to be very problematic. Right? As we'll see, this is going to make life very hard for the machine learning algorithms, and it's going to make life very hard for you. Right? How do you look at 100 million pieces of information about somebody? It's going to take too long. So the very natural idea in dimensional reduction, as the name implies, is that you want to reduce that number of dimensions. I don't want to be looking at 100,000 pieces of information. I want to be looking at, a dozen, or maybe even 3, such that I can plot it, in 3D, or even 2, or 4 if time is one of the dimensions. So dimensional reduction is the study of how to take examples with many, many dimensions and reduce them to the most informative dimensions. Okay? And again, this is a very active area of research these days, many fascinating algorithms being invented. We will just have time to cover the main ones and to give you a sense of the power of this type of machine learning. Okay? All right, so before we go into